So my name is Veli-Pekka Ketonen. I'm from 7Signal, and 7Signal is an Ohio-based company. We are originally from Finland, but we moved over to US 2 years ago. So 7Signal is a performance management company for Wi-Fi. So that's what we do. That's what we focus on. And I myself, I'm an RF guy from my background. I've been working a long time with Nokia networking side prior to 7Signal. So that's what I have been doing. And the performance management has been a long time something that we have been working on. So I have several topics today what I would like to cover. Let's see how much discussion we can get here around these themes. If there's a lot of discussion, we can focus on those points and then maybe go faster certain other areas. But I wanted to add here in the beginning a short overview how 7Signal product works. Because there is later on data that I will show you, and then there are observations and best practices that we have developed that are based on this data. So I think it's useful for everyone to understand that how the data collection works. So I want to cover that first. Then I have several topics there which I think might be useful, thinking concepts. Some of them have been already mentioned here, and I'm maybe highlighting some new ones as well. So I hope they might be something useful, and I want to cover those. Then we follow certain practice when we optimize Wi-Fi. We have certain steps. Obviously, they are not always the same steps, and the order varies, but anyway, there is a certain systematic process that we use and what we follow on how we improve those Wi-Fi networks. Then I have some selected data from a few networks showing you graphs going here and there, up and down quite a bit. As well, I'm highlighting a couple of, Keith, we got started already, if that's okay. Good. So highlighting some new technologies that might be coming over to Wi-Fi, some of them sooner, some of them later. Some of them you might have heard of, some of them you might not have yet heard of. Some of these are discussed with the IEEE High Efficiency Wi-Fi initiative there, which is starting or ongoing, soon defining the scope for the new standard. So I have picked a couple of ones from there. So that's what I want to show you today. So first, the key principles with the product that we have developed and what we offer. So we have a sensor. It's not a passive sensor. It's at times passive sensor, but at times it's as well an active end user. So it's an automated end user in the network. So that sensor is placed among the access points. Sensor has a beam steering. We have there 7 patch antennas that we use to steer the beam, so it's pretty strong beam steering towards different directions. We have one radio in that unit, and we do the beam steering thing. So when we collect data from the network passively, we do packet capture, and within the sensor or eye unit, as we call it, we calculate matrices within the unit. So we are not usually streaming back all the packet flows, but we calculate the metric inside the unit and then send the metric back to our server. So that's the passive part. Then there is the active part. So the sensor is the active end user emulating end user traffic. through the access points that are surrounded by the sensor. And this way we measure the wireless and wired connection over the network, and we get continuous data, days and nights, how the network is doing. So in addition to this eye or the sensor part, we have two other parts with the product. So the other is Carrot, which is the engine, collecting the data, having the database there, offering user interfaces, so all that. And then the third element is Sonar, which is a test endpoint. And there can be several of those. If you want to measure between certain sensor and certain test endpoint, it's a software running on a server, so you can have several of those. So you can mix and match and measure across the network how your network is doing there. So you get trends. We continuously measure the network the same way. So we always, once assigned, we use the same antenna. There is an AP, so we use this antenna for that AP, and we automatically do that continuously, always the same way. So if something changes in the matrices, it is the network. Okay. So we have a various type of measurements there that we can do. So those synthetic transactions are really the key. We get continuously samples how network is doing. Passive packet captures and metrics is calculated based on those. That's very important. Then, Then more general RF analysis, signal levels, noise levels, and so on. So that's one of the areas. We can do as well 2.4 spectrum analysis with the beam steering, so we actually can see from which direction interference is coming from. So there is the directional capability what we have there. And then remote full packet captures, if you have to. Yes?
So when for your synthetic tests with your voice quality measurements, what codecs do you use?
For the voice?
Yes.
I think it's, is it the G711 or the standard voice VoIP codec?
We see a lot of customers really using products that use silk.
Okay. We have there some variability. So how we perform the tests is so that we have a test scheduler, and then we have a standard tests, and each of those tests you can configure. So you can take this certain test, parameterize the test, place it to the test profile, and then it will be part of the tests. And there are variables. I think the codec, for example, is one of the variables. You can vary the codec. So, yeah. We do calculate MOS scores. We use an algorithm called PSQA to calculate the MOS scores.
Does that Sonar allow customers to load their specific environmental applications to generate traffic that they expect to have on their network, or is it generalized?
It's you can choose from the tests that we offer different protocols that you want to test. So we have a number of different tests available, and those run there. You can as well download certain, for example, a company homepage. You can measure the throughputs and accessibility. You know how successfully you can download. How long does it take to download, for example, the website? So there are a number of things that you can vary and configure. But on the other hand, it's not so that you could take any application and yeah. Okay, so we have a lot of matrices, and all of them have time axis. So that's the key. I'm not going to go through this, but we cover from layer 1 to layer 7 a lot of different matrices. So that's how we get the data. That's how we measure the network. Now, I picked now a couple of points here that I want to bring up, and I hope they are useful. Some of them are familiar, some of them might not be familiar, but first of all, first thing to do when you want to enhance your network performance, we have found that it is very important to understand the radio environment, what you have there around you, and do what you can to organize it. Some key things are really that you really want to stick to your channel grid. You don't want to have those APs in between there. They are bad. Ad hocs or neighbors or what they are. So they are not good for the performance. Definitely, there are collisions and there is a high noise and you start dropping packets, you start getting retries. So not good. And different capabilities there obviously interact there in live networks like G and N, different access points, B. So the number of SSIDs or ESSIDs or APs in general per channel obviously is a very key. You don't want to have a lot of them. Increases utilization and lowers the airtime for clients. The second one is the antenna. This has been discussed. Antenna is very important when you want to prevent the spread of energy to certain areas where you don't want it to go to. So, and the placement, you want to have the line of sight always when possible, not to put it above the grid, but below. You don't want to have anything near the antenna, nothing really, if you want to make it perform well. Antenna radiation patterns, they are always tiny, but then there is a 5 dB grid, and it seems like it's nothing. It is a lot, and it makes a big difference where that gain is pointing to. Is it pointing sideways to the next AP, so it's maximally interfering with the neighboring APs, or is it pointing down? In some cases, it's good that it points straight down, but most often it's good that it has some down tilt sideways. And the antenna gain is bidirectional, so that's almost the only way to enhance the uplink direction from client to your AP. So you can use the AP antenna gain to pick up the signals better, and that will help as well clients use higher data rates. So that's important. Then RF power levels. It's actually not a very simple thing. I mean, there are a lot of variables with the RF power levels. So you have the conducted power coming out from the radio. You have antenna gain that you put on top of that. But then it starts to be more complicated because you have variables. You have HD20, HD40, HD80. Your power levels will most likely vary depending what bandwidth you are running there. To make it more complex, your power levels will vary depending on what MCS rates you are running there. The linearity of those transmitters isn't always very good, so when you use the highest rate, the power will go down, and that's kind of that's when you mostly need the high power. With the highest rates, the transmitter power will go down at the same time as the rate goes up. So it makes it easily kind of oscillating, and you get a lot of retries because the power goes down at the time you would really need actually a better SNR, not worse. Then there are different ways to tell what is the power level. I mean, sometimes it's the combined power level of each chain, and if you are using 3 streams, then usually the power level includes the gain you get by combining those 3 streams together, like a diversity, downlink diversity. But it's not the same as adding power. It adds robustness to the radio, but it's not the same as adding more power. So there are a lot of variables. Something which is completely missing from the specification is linearity of the transmitters with the wireless radios. which is the best metric for that is error vector magnitude, which tells that how clean is the signal that you transmit. So how much is it distorted already when it is transmitted out. So that's never really specified. So another one way to help this is to lower the output power so that you get support for the maximum rates with the power level that you use, and then use more antenna gain to compensate for the lower power level. So you get the maximum rates with that power level that you want to operate, and no fluctuations. But a lot of, and then sometimes clients or APs might have to drop power levels at the band edges because they might not pass the spectrum mask test there. So there's a lot of things that power level isn't always what you think it might be. Sometimes the power level is not back annotated correctly. If you have an automated power control, it might not annotate it correctly back to your controller. So you might see their value, and if you fix the value to the same value, power might change radically. So a lot of things. Then retries. So these are from 2 papers. Let's see. So different modulations have different speeds at different signal levels. So rate control tries to always pick the best rate for the conditions that you have there. And it's a tough task, but that's what it tries to do, continuously varying the rate to the optimal one. So you really would like to reach this kind of curve so that you use the best of all rates always. But that's really not happening always. So there's one paper made by Georgia Tech here illustrating some of the differences for the goodput, which is the end user throughput, and then the kind of manual setting, and then the auto rate setting, the rate control setting. So rate control would be a very good place to improve the performance. And it is for access points very hard to do because each client needs different rate. For clients, they know what rate they were using previously, so they don't care others' rates. So it's very tough for the AP to pick the right rate. But it would be very important to have the right rate always. So retries in the radio and the data rate used there, you can make a lot of conclusions based on this data. So first of all, if you have a high retries and you have a low data rates, you know that you are at the coverage edge. So even though you are using the lowest and most robust codec, the packets are not going through a lot of retries. The another scenario is that you have low rates but low retries. It means that, well, it's low rate but it's going through nicely, so you are using the right rate. So capacity is limited, airtime, throughputs per user are limited. Then the optimal is having low retries, high rates. And obviously, each client and access point chooses the rate by themselves. And your goal is to help clients and APs use high rates. But unfortunately, often devices use higher rates than they should be using, and that causes a lot of retries. So if you have a one retry, you just double the time it takes to, get the packet over, and retries can be repeated from 7 to 25 times. So it's a lot of airtime if it's not going through. So retries, data rates, very good indicators overall. Then power control settings. So if you use automation there, Sometimes they might drift to one edge or one end, maximum or minimum. Quite commonly it might end up to being minimum value. So it's good to limit it somehow so you know that where your power levels are if you run the automation there. Especially cases where the APs can hear each other as well. The automation sometimes has trouble with such cases. Channels, another very important thing. So you want to make sure that you evenly distribute your channels. So if automation ends up using the same channel in the nearby APs, you are losing capacity. Sometimes there might be a good reason. There is so much noise that you just can't use the other channels, but that's often not the case. So it's good to check that how good is your channel plan. Most controllers can show you that on a map. So the key here, and as been discussed as well elsewhere, is to use as many channels as you can. That's your best way to increase throughputs and capacity. Allocate more spectrum. If you have like 5 GHz channels, if some of the clients possibly do not support 5 GHz channels, certain channels, if you have the same SSID on both bands, it may, if a client doesn't support that channel, it may jump down to the 2.4 in those areas. But overall, the result will be positive. So sometimes channel automation may go wild and just go everywhere. So there are ways to stabilize that with the parameterization that is offered. So that's something to look at. Well, legacy mode, B, very significant impact on the performance. So if you have B enabled, really look hard, do I really have to have B enabled? Can I disable it? Very significant impact on the performance can be many-fold in end-user throughputs. So one aspect is that TCP protocol doesn't like lost packets. So there is a mechanism in TCP called a slow start. If TCP experiences a packet loss, then it will hit the brakes and start slowly increasing again the rate it puts out packets. So if you lose your packets at radio, TCP is not going to like it, and your applications will suffer. So and this slow start is behind that behavior. So one way to look at the retries is here that you can have retries at the user level. So you click several times the web page to get it. And well, that's one retry. Then there is another retry. Your application might be resending packets as well if it's not getting acknowledgements. TCP will be resending packets. And eventually the radio will be there, resending packets 7 to 25 times. And if your rate control is always using too high rate, think about how much unnecessary traffic that puts to your air. So it's incredible amount of air time needed. So for UDP, that's even worse, because UDP doesn't retry. If your radio is not delivering the packet over, the packet is lost, and your application is not really performing really well. Another aspect to performance is the fragmentation. So you can fragment the radio packets. The larger is the packet, the harder, and the probability of getting it through properly is lower. So, but obviously the efficiency is better if it goes over first time. So, but Wi-Fi is such that you have to receive the packet completely clean. So if there is one error, send me over the whole packet. It doesn't combine recent packets. It only acknowledges completely clean received packets. So that's one kind of efficiency thing there. So you can fragment to smaller packets, obviously more overhead, but if packets go through better, overall performance will be better. Yes?
You mentioned aggregating, like reduce robustness. So we know that the 2.11ac now will do block acknowledgement.
Yes.
Because it will transmit block mode.
Yes.
That means that AC will not be as robust as N, as an example?
Well, there should be automation in place to do that, but if block acknowledgements are used, it means that you have to receive several packets, and then you get one acknowledgement that acknowledges that, yes, I got these 3 or 5 packets clean. But if your block ack tells you that, no, I didn't get all those, so radio has to retransmit them one by one, and then acknowledge usually packet by packet. So it is more efficient if it goes through at once, but if it doesn't, it causes these retries and overhead again. So optimally, the rate control and these different functions like fragmentation, these should work together in such a way that it results the best kind of user throughput. But I don't have yet much experience with the AC, so I can't say, but the block ack is in N as well. But that goes the other direction than fragmentation. So it's good to kind of acknowledge that this is what it does. Okay, then one thing to help again is the QoS. So you can use higher QoS class to prioritize your traffic higher than the others. And if you are running your Wi-Fi in a place where you might have some ad hocs or some rogue APs, which you can't manage, so I would say it's pretty fair for you to run the higher cost class because you have the real network that should be run there. So that will help you to achieve better service quality for your end users. Vendors have different implementation for the QoS. Some of them try to identify the stream and apply the right QoS, some not. But there are functionalities. If you assign a voice cost class to your SSID in a noisy or busy environment, it will improve its performance. And this is one tool, again, in your toolbox. So those are the concepts I wanted to cover, and it's a kind of toolbox that you have available that you can use to improve the network operation. So next, I'll go through our flow. How do we look at the data? How do we conclude things? How do we optimize networks? So couple of things there that you need. So you need to have the data which represents end users' view how network is serving your users. And key metrics there really are how well are the bits moving and how well are they delivered. Throughput, packet loss, jitter, latency, usually the really key ones. You need knowledge, so you need to understand the basic mechanisms there, what's happening there in the radio to make the conclusion that I think I should try this because I have this kind of problem. You have to implement changes to your network based on the analysis that you have done, and and then analyze what is the impact of the change. So after each change, you will learn, and it's very important to learn from each change. Yes?
So would it be safe to say all of those steps you talked about in previous slides are like ingredients for a recipe, and you're using this to determine what the proper mixes are?
Exactly. In your network, because all networks are different. Yeah, they are the kind of tweaks that you might consider. I have as well some additional ones here. So overall, the process, what we use is that we look at those active measurements that we collect continuously. We get the data. Key matrices are the throughput, packet loss, latency, jitter, success rates. And you have the time axis. You get data as well nighttime. If your network isn't going fast nighttime, when there is nobody possibly using it, depending on the application, of course, if it doesn't go fast, something is holding back. And you need to find out what is that. So the assessment comes down from the application layer to the radio layer, and the optimization, as we think it is best, is to start from the radio layer and start from there to enhance capabilities like channel plans, utilization kind of things, and then make those changes and observe the impacts at the application level. So it is a loop, continuous loop, where you enhance and keep the performance at certain target level. So this is a little bit a busy picture, but here are 10 steps that this is one way to see what you can do, how the process flow goes. So you get your baseline first. You need a couple of days data, because usually you have trends, like a daily trend, weekly trend. Weekends are different than working days. Daytime is different than nighttime. So usually during the daytime, your throughputs come significantly down if you have a lot of clients. At nighttime, it goes again back. So you want to see a few trend curves to understand how you are doing. Then channel plan is the next one. And so you try to allocate channels optimally there. Use all possible spectrum you have available. Very important for maximum capacity. Minimizing utilization, many ways to do that. B is one of those. Try to avoid the B, enabling B standard. Well, I have a slide for each of these. So you will, by the way, get this slide deck. There will be, at the end of the deck, there is an address you can download this. So I'm not going to go through all the details, but this utilization is pretty important topic overall. So you should always try to limit the number of SSIDs. Really, you should not have more than 3 to 4. It starts to fill up the air, so that you don't have space for your data packets anymore, especially if you run low rates or B even. And you have a dense beacon in 100 milliseconds, which is really actually pretty dense. So what you can do is reduce the number of SSIDs, remove B rates if you just can, remove support for lower MCSs even, or other legacy rates. You can send beacons at higher rate or at higher intervals than 100 milliseconds. This one you have to be a little bit careful with, because some, especially voice terminals, assume that you get this 100 millisecond beacon interval. Yes?
What about altering D10?
Yeah, you should, when you change the beacon interval, you should set D10 to 1, because you want to still have the information regularly enough. So if you have...
If you don't change D10 at
that direction we haven't tried, but we always, if we go from 100 millisecond to 300 millisecond beacon, we change DTIM to 1 to have the updates regularly enough. Sometimes power save in the APs will consume some memory there, capacity.
What about ARM and RRM messages?
RRM messages, you mean?
So Cisco RRM and Aruba ARM send at a lower data rate, but they don't send as frequently, but you can also back that off too.
Well, I don't have experience with that. I don't know how significant that is, but that's exactly one thing that you should look at. Is this significant? Does it help if I change this? So we don't know all and everything, obviously, but we get the data. So if we change something, we get to see what is the impact.
Yeah, because you're independent of your data rates. So send that one typically, because when you have enabled on the network.
Yeah. Okay, good. Very good points here. So and I'm sure there are others as well. But one important concept is, again, here with the utilization, is the clear channel assessment threshold. So that's typically minus 85 dBm, minus 82. I think standard says minus 82 for the wireless LAN packets. So it means that that if when you assess is the channel available, that's the limit. So if the packets you get there are lower than that, then you just go ahead and transmit. If the packet that's going on there is higher, then you have to wait and back off. Try again. If you increase the threshold, you will get more transmit opportunities, basically. You will override, but overall that will increase your airtime and availability. One thing to consider is that if you use directional antennas, you are efficiently lowering the CCA threshold because you are amplifying that certain direction. So that's something to think of. If you have a high gain antenna, you might want to, because you are possibly not using full downlink power that your antenna uses, but it sensitizes, makes your receiver clearly more sensitive, so you are losing airtime. So you might be too careful with the transmit opportunities. So going back to this overall flow. So power levels, obvious one. Then interference. Of course, you want to get rid of all the interference that you can, but unfortunately, often it's real hard. I mean, if you have some analog video cameras that shouldn't be there, or other devices that can be removed, always they should be removed, obviously, if you just can. But often you just have to live with the interference. And I understand how remarkable is that. So you can improve radio robustness as well if you need to fight the interference. So you can start, because rate control tends to use a little bit too high rates, so you can remove the highest rate. It will improve your goodput with less retries, more reliable connections. You might want to run voice on G or A only. If you have a separate SSID, packets go much smoother through. That's what we have seen. You assign higher QoS class. You get higher priority. And if you have noise there, high-level noise, that will kind of override, go through the noise. Fragmentation, another way to handle and fight the interference. And some equipment as well provide a interference-resistant mode. You can try that. It probably fragments packets and does things like that. So there are ways to fight the interference and cope with that.
Can you explain why not use N for voice?
For voice, well, N maximum codecs are more sensitive for the noise than the G and A. So 54 is more robust than MCS 6. Yeah.
I understand the modulation part. What about the efficiencies and whatnot? Well, voice is a component.
There's some funds, or some things that we decided
I've actually seen that.
Sometimes if you have interference that will actually run pure G or pure N, sorry, pure A. There's some let's say, VLAN vendors where they have problems with that.
So with ISO clients, you see an improvement.
Actually, it's the voice packages are very small. I believe it's actually faster to send them with a G header instead of a mix header. Because the mix header is much bigger.
Good point. Very good point. Okay. Yeah.
So you can receive an N packet, but it's an answer with a G packet, for example.
I think Andrew made a similar comment earlier about looking at high rates in adverse situations, and we do the same thing. That's a best practice guidance in very challenging environments for the same reason. Also, you could interweave, with the virtual AP concept, right? So you can have a voice SID on the same radio as, a data SID, for example, and these settings can be applied just to the voice SID. So you actually can interweave both types of traffic. It might be a second, but if you have that ability, then that gives you the ability to kind of thread the needle and have the best ability.
Yeah. Yes. Since we deal with clients who have their own infrastructure, that we can't pick their infrastructure for them, we do what they have. So that would be lovely if we could do that.
Okay. All right, so a couple of steps to go further. So you can improve the robustness of your radio by doing tweaks. You can prioritize traffic, and that's obviously one way to do that. There are different features and ways of doing that. And balancing traffic, if you do manual power plans for the Wi-Fi, so you assign static power levels, when you move the power levels relative between two APs, for example, which have a lot of, the other one has a lot of clients and the other one doesn't, you a little bit vary the power levels they have and all clients go to the other AP. So it's a very efficient way of balancing the traffic there if you do manual power plans. Obviously LAN, so I mean it's just one here, but it's a long way usually that the wired carries the traffic, so have to make sure that that as well works, very important. And client operation, of course, there are ways to improve client, and sometimes clients are in an enclosures, very often actually. Somehow the antenna is near to metal, within a box or wherever. It's clear that it doesn't work very well in that kind of conditions. And then eventually, if you are not getting there with the tweaks, adjustments, you may need to move APs, add APs, change APs, upgrade software. I mean, software upgrade is probably something you want to do pretty soon, but you might need to do physical changes to network eventually, obviously, but you want to have that as a last resort because it's usually most costly thing to do. All right, so there are more details here. You can go them through. More tips, tweaks. but every network can be made to perform. That's clear. It may take several rounds, take time, understand what is the bottleneck, but you can make it run fast.
He did a stress test in different APs with a different amount of clients were behaving radically differently.
Yeah.
And this sounds like the Ketonen point narrowed down exactly what the behavior is.
Yeah. Yeah.
Make it more visible. You don't have the tools to.
Yeah, what we should have done was have the 7 signal watching while we did it.
Yeah.
And then you could decide what happened. That's what I was going to ask you. So your product, I mean, obviously you're giving a talk on some of these best practices, how to clean things up, right? Is your product going to give you that feedback? I mean, is it calculating and stuff saying, you know what, this is what we see, so we should do this, you know, pretty much what we just saw.
Excellent question. It does now. I'll have a slide on that. Very good point, because there's so much data. So making the conclusion, what is the right call? What should I change? What is the bottleneck? Identifying the bottleneck automatically is very useful. We have now a feature for that we just released. So it's not only getting the data, but analyzing it automatically and suggesting changes that these are the areas you should look into. Make the tweak, look at the graph data. Is it improving or not? And keep going. So very good point, yes. So some example data here. So, so this is from a hospital. This already back from 2011. So what you see there is each line is one access point. Each sample here is on daily average. So it puts together all these samples from that access point for one number. And then we have a number of changes we have implemented here. So, oops, I don't dare to go there. That's loud. So you can see we started here. Throughputs, this is uplink throughput in active measurement. Sensor sending packets and data through the APs. Oops, we implemented a number of changes based on the observations. So first of all, we changed some of the antennas. So throughputs came into better range. We made some channel changes, so better channel plans, kind of improving power level changes for the APs, so improving, or maybe staying pretty even there, this metric. Then codec changes, we disabled lower codecs, lower utilization, and finally we noticed there was a bottleneck in the core network, so they added there some capacity to certain links. They were hitting high load and peaks, and certain times of the day it was losing packets, especially nighttime when they run backups there. So the VoIP call quality went down significantly. So this is the uplink throughput, and this is the voice quality over the same changes. So you can see that after the first change, antennas, it got worse. So the antennas were better radiators, so they were radiating everywhere, and the radio wasn't coordinated, so performance got worse. So after we worked on those other steps, it narrowed down, straight line, 4.0 perfect MOS score on daily average level. So that's what happened. Another view to the same is packet loss during the active measurement. So you can see how the packet loss came down continuously when we made those changes. So different matrices react differently to the changes.
Question.
Yes?
Is this taking into account roaming?
These are not roaming matrices, no. So, yeah. Then I have data from Avans University of Applied Sciences. So case is actually here, so over there. This is from. So 5 gigahertz data. So what we have here, again, a number of changes. 2 lines, 2 floors. Each of them having several access points. So now the data has been combined so that there is 1 line per floor and 1 sample per hour. But it's all the APs in that floor put to 1 line. So 2 floors And these are the changes we implemented there, and this is the behavior we observed with the matrices. So pretty significant changes. So that was downlink throughput, FTP or TCP throughput. This is HTTP throughput over the same changes. This is downlink MOS score. So the dots here, kind of dips here, this is a 1 hour average sample. So at times it comes down certain times of the day, but we kind of got them moving up. Round trip time, daily average values coming down significantly. I mean, from 4 to 2 isn't, it seems like it doesn't make any difference, but if you look at the hourly levels, daily time they are way up, and night time it's down. So the average is here, daily average. Radio retransmission rates, how they behaved over these changes. So over these changes, we got them coming down nicely, and when we enabled HT40 here, they went up. So not the desirable thing, but overall it worked better, but retries went up. Possibly power levels went down, and this caused this happening. And this is from the clients towards the AP. Same thing, the other direction, clients sending packets again and again to the AP, and the same kind of behavior there. We see often that this client rate is much lower than the AP retry rate, so that's something to think of.
And this is data you're gathering from passive scanning?
Yes, this is passive, yes, absolutely. Yes, this is the actual client traffic. Okay. Yes. Another view to the data before, after. Another metric, another university, similar trends there. So this is busy, but again, there are several floors, each including several APs. This is the hourly average and all of them. So these are interesting, these drops here. So what happens to these minimum hourly values? They went significantly up here. So some example data there. Then I have a few minutes left. So wanted to cover some very interesting opportunities for improving Wi-Fi performance. First of them is asymmetric priority control. So you can apply different backups and retry, different backups and priorities for the AP than for the client. APs send much more packets than the AP clients usually. So if you give AP more priority for access in the air, the overall efficiency will go up. So there are some papers on this. For example, WYFOX is one of the papers that's been published on this one. So another one is a dynamic sensitivity control. So the radios automatically vary the CCA threshold in relation to the signal levels. So by doing that, you increase, again, transmit opportunities there for the clients and APs. Again, another one is full duplex Wi-Fi. It sounds like you can't transmit and receive at the same time, but guess what? It's possible, and it's coming. So same frequency, transmitting, receiving, same time. It's possible. The dynamic range has been issued there, but they're getting there with the analog and digital cancellation. So it's coming. So might take some time still to get APs from vendors, but you know, standardization body IEEE is looking at this. Multipath TCP. So you can have several TCP connections. For example, Siri uses multipath TCP when possible. So 2 paths over the network, more reliable connections. And then overall self-organizing networks, automation for doing all this continuously, automatically. instead of manual adjustment. So, of course, Wi-Fi has already some automation, but I would say that results are still mixed. It's not really yet optimal. There is a lot of room to improve, in my opinion. So there is a link here. If you click the link, it opens IEEE Hue library, so you can see all the presentations. Extremely interesting presentation.
In the case of multipath for mobile devices, for most cases, the second link is the cell connection.
Yeah.
You're looking to add, at some point, cellular monitoring, some way of being able to track that because it's going to your carrier, because they may still be using that to access info.
Yeah. So are we going to add that kind of functionality?
Right.
Yeah. We have been thinking about it because obviously they are kind of merging together, but we don't yet have a product for that.
Sure. No,
yeah. But it is definitely a valid point. Absolutely.
Can you just briefly describe the full duplex? So I think there's some proprietary bridges out there not using 802.11 that can use full duplex on multiple channels. Can you explain how full duplex?
Yeah. Yeah, so and I think this is more like for the AP because the cancellation is pretty complex. So when you transmit, you will in the receiver you can cancel the transmitted signal form two ways. So the first one is analog way. So you take the RF wave that goes out and you inverse it and apply it back to your received signal. So you get a 40, 50 dB.
Noise cancelling headphones.
Yeah, same thing on the RF side. But that's not yet sufficient. So you need to have some digital cancellation there as well. So you, on the baseband, you know what you sent. So in addition to canceling with the RF waveforms, you can cancel with the digital part further on. So you get 90 dB. I think it's over 90 dB dynamic range there, cancellation, so it starts to be enough for transmitting, receiving same time.
Is that part of 802.11q?
Yeah, it's one of the proposals there. So these are not something that are promoted there by the standardization, but I kind of like these, so I picked these. Yeah. So yeah, one slide about this automation. So we have built a feature that does the automation, or analyzes automatically. So it ranks the bottlenecks you have in your network to I think 7 areas. Then there is certain priority, certain order, certain ways to calculate that, and then it creates a plan that these are your most important things you should do about those and make suggestions. It is not a vendor-specific suggestion, but it might be like your most important bottleneck is that you have a lot of non-organized RF buildup there. It seems this is your number one thing, so do something about it, try to. And then there are ideas how to address that. So. And you can export that to PDF and you kind of ready plan. So that's it. So I mean, overall Wi-Fi, incredible technology. So you can put it together and put it in a metal box and wherever it works somehow often. But if you want to make it work well, it takes a little bit more. So you want to allow it perform well. And by doing this in a systematic manner, pragmatic way, is it helping or not, you can do a lot of things there. So that's our experience on this. So thank you.